Hello everybody. In today's class we are going to continue with the introduction to microprocessors, which we started in the last class. Today also we are not going to get into specifics of 8086, but we are going to discuss in general what a microprocessor looks like and the basic functioning of a microprocessor. In the next class we are going to take on 8086 and we try to get into details of 8086, right? So last class we discussed, okay, for any computer, whether it be a desktop or a laptop, the heart of the system would be a CPU, central processing unit, or a microprocessor. And then you require certain inputs, which could be in the form of a mouse, a keyboard, or a mic or a camera, which will provide the inputs, various inputs, which through an interface unit, and those inputs would be given to the CPU. And also we require a memory units wherein we write the programs, and the CPU can fetch the data from the memory as well as can write data into the memory. And finally the output of the computation can be sent either to the memory unit for storage, or you could have an like outputs like displays, or you could have speakers, printers and things like that, right? So this is what we discussed in the last class. Building upon that theory a little, getting into little more details of what a memory looks like the memory can be again classified as primary, secondary, cache memory, and there could be some registers also. When a CPU is given by the manufacturer, certain programs, which is known as the firmware, like including when you power on the CPU, right? So the microprocessor has to run some built-in checks and things like that. Okay, so that is specified, that is very specific to the motherboard and the chip, and provided by the manufacturer itself, right? So that we can't do any changes in that. So those things are available in the ROM. ROM stands for read-only memory. Now these ROM, earlier it used to be in a PROM, EPROM, and now it is electrically erasable and programmable ROM. So in this EPROM, so you don't have all these three together. Okay, we generally have only EPROMs available now these days. So in the EPROM, the manufacturer provides all those critical programs which are required the moment I switch on the CPU. Okay, also when the CPU is running, constantly when the CPU is running, there might be some sensors, like it might be monitoring the temperatures, conditions of the batteries and things like that. Okay, and whenever there is a problem, the CPU has to take necessary evasive action, right? So remedies, some remedies might be suggested by the manufacturer. So all those things are not in our control. Okay, they are already programmed, and those programs are available in the EPROM. So when I say a ROM, it is non-volatile. That means even if the power is switched off, those programs will be retained here, right? So that is there. And since it's electrically erasable and programmable, some portion of the EPROM is used for a BIOS setting. Okay, that we can also change that portion of the program. Like for example, we would want like when we have more than one or two hard disks or one or more operating systems, we can do those BIOS settings, right? So which is the one which the CPU has to, after doing the initial built-in checks and all, which is the operation system which requires to be loaded. So all those kind of a little bit of programming at the user level can be done, okay, in the EPROM. So this is a read-only memory, right? And then our whatever is the main program which we write, right, that needs to be stored in a secondary memory. Okay, it could be hard disk, right? These days we have SSD hard disk or magnetic tape, CD, DVD, etc. Okay, the main program will be there. Now when the CPU is running, if the main program is available in the hard disk and I need to fetch data from there, okay, so these are all very slow devices, and this is very large. Okay, so it will take time for it to go to the particular memory location and then fetch that memory and keep running. Okay, so what a portion of that hard disk or memory which corresponds to the present operating requirement. Like if I am running some, say say right now I am opened up an presentation, right? So some portion of the present Microsoft Office will be loaded into the RAM. Okay, similarly some data could be. So some portion of the secondary memory is always brought to the RAM. Okay, so that RAM can be easily be accessed by the CPU. Okay, so it won't be that easy. It will be time consuming. So it will slow down the system if my program resides in the hard disk. So that is why we say as we keep increasing the size of the RAM, right, more and more program is brought, the quantum of the program from the hard disk can be brought into the RAM and made easily accessible to the CPU, right? But you can't have an, if you make the RAM as big as a hard disk, then the purpose gets defeated, right? Because only if this is a small thing, right, only then we can easily access it. The moment I make this as large as then they become the one and the same, right? So these RAMs are generally smaller and they just have to have a capacity to store the required programs at any given time, right? Secondary disk can have a lot of data and there is no limit to what can be stored there, right? So RAM is depending on my usage. So my requirement of RAM will be different from that of somebody else, right? So depending on what kind of softwares I am running. So that is what. So this is read access memory, and since once you switch off the power, nothing will be stored here. Okay, so everything will be stored in the only a portion of the from the hard disk will be brought here, and then you need to save it. So nothing remains here. So the moment you save it, some data that is stored in the hard disk. Okay, so nothing can be stored in the RAM. Now you may or may not have both these kinds of RAMs. There is something known as static RAM and a dynamic RAM. You will learn it in your VLSI classes. You could refer to some of my VLSI design, advanced VLSI design course. Okay, if you are more interested in knowing how these things function. Okay, now static means right, this it is like a cross-coupled inverter where once the data is there, it will remain there as long as the power supply is there. In dynamic, the data is stored on parasitic capacitances. Okay, now the thing is just to understand for us for the time being, static takes it is faster but it takes more space. Dynamic is slower but it is very high density. So right, these days we all have DDR RAMs, right? So but they are slower than the static RAMs. Okay, so that is what. So many modern day processors, they also have a cache memory. Okay, what's a cache memory? That some data which is very often taken, okay, very important. Okay, those data can be placed in cache memory, which is generally static RAM in nature. Okay, that is like you could call that as a subset of RAM only. So some data which is very frequently accessed. Okay, so that can be put into a cache memory, and some data directly, if you want to put it into the external bus or so that also can be done through the cache memory. So they are generally of static in nature. Okay, static RAM design. Okay, whereas this RAM is generally dynamic and cache memory is generally static type, because here the requirement because RAM, if I have to have a 32 GB or 64 GB RAM, so I might want to go for a DDR dynamic RAM which doesn't occupy that much space and consumes less power. Whereas cache memory, I don't have to have that large memory. Okay, I could have only say 1 MB or 2 MB or 1 GB kind of thing, where only very critical data is placed there, but that has to be super fast, and hence you could have a static RAM here as a cache memory. Okay, so this is how this is the basic block diagram of a computer with some input about the memory. So what happens? So what our CPU is supposed to do, as soon as I give an power supply, this is supposed to take the program which is stored in the EEPROM and done a built-in test. Later on, from the EEPROM itself, I have a BIOS setting which will tell me where to load the operating system. Okay, and once the operating system gets loaded. So now from the hard disk, that operating system, some part of the operating system will be brought into the RAM memory here. Now the CPU keeps communicating with the RAM. Okay. So and also you could have a cache memory where there is a requirement of frequent access of data. Some portion of the this program can be pushed into the cache also. Okay. So this is an overall block diagram of how a microprocessor works. Next, let us see what is the difference between a microprocessor and a microcontroller, right? Essentially, microprocessor, we said it has got an arithmetic logic unit. It will have a control unit. Control unit basically fetches the instructions from the memory, and then it controls the ALU, and it puts data into the registers, and also it gives the data back to the memory. So the entire controlling is done by the control unit. So this is a microprocessor. When we talk about microcontroller, this entire microprocessor is represented here like this as a CPU, but this CPU will not be as strong as a microprocessor. It is a scaled down version of a microprocessor. It won't do those many, it won't be that fast, and also it's a weak microprocessor, you could say. It will do a limited number of functions. Okay, but then it will have a RAM, internal RAM. It will have an internal ROM, where in the ROM you can feed that. It could be EEPROM also. You could program it. You can feed your code into the ROM so that it works independently later on. So it will have counters and timers. So essentially a microprocessor controller, you could call it as an mini computer, whereas this is just the computing portion. Okay, it is just the CPU, you could call. Microprocessor is essentially just a CPU, whereas microcontroller is the entire a mini computer. Okay, it can do tasks independently. So this is the basic difference between a microprocessor and microcontroller. What I am going to do now is I am going to play a small video of 10 minutes. This will give a fairly very good idea about what is a microprocessor, what is a microcontroller, and system on chip. Okay, so let me just play this video for you. You may now pause this video and watch the video from the link provided, which will give you a fair idea about the difference between microprocessors, microcontroller, and system on chip. So continuing with that, this is what is an 8086 motherboard looks like, right? There is an 8086 chip out here. This is the board. So you will have a keyboard to punch in data into the RAM, right? There could be an EEPROM, wherein you can permanently store data, or there could be a RAM, where in the lab generally when we do experiments we dump the data into the RAM so that it does the execution, and once you switch off the power supply, that program is no more there in the kit. So this is a microprocessor and a board. Okay, it has the processor is there, and then you have a small circuit which will generate the clock. You will have an address latch. All the ICs are over and above the 8086 chips. This is just the 8086 chips, but you require all the interface chips are all outside on the board. Okay, this is an Arduino microcontroller. If you see, this is a controller which is kept in below. Almost there is no other, although it is spaced out like this. This doesn't have large number of peripherals or associated ICs here. Okay, these are all only the IO input output ports are brought out to the different pins. There will be small power supply regulator. So this itself, so it has got essentially all input output ports. You give inputs and you take the outputs from here itself, and you program it, program the Arduino. The memory is within this chip itself. You are going to dump the program into this chip, and once you run it, and you just have access to these pins, input and output pins. Okay, whereas here if you see in a microprocessor, this is the chip, whereas everything is external to it. SI had a microprocessor designed for specific task, while SOC is microcontroller is designed for a specific task, but SOC is little less powerful than microprocessor. See, microprocessor is the most powerful one, right? Okay, after that it comes microcontroller also, because microcontroller is also not for a specific task. It can do a wide variety of tasks, but you will program it for a specific task. Okay, whereas SOC is not for programmable. It is generally made for a specific task. Like if you have an Apple mobile, so the chip inside that is an SOC which is designed for that particular Apple mobile, right? There will be a different SOC for an Apple tablet. Okay, it is again very focused and targeted to work efficiently in the tablet, right? You can't put that SOC elsewhere. Whereas microprocessor is obviously, it has got full freedom. Microcontroller is again, it is programmable. It can be used for a wide variety of things, but then it is not as powerful as a microprocessor, but then it is a mini computer. Okay, is the difference between all of these three clear? Anybody else has got any kind of doubt? No? Okay, so let's move forward. This is a microprocessor, right? Now we'll again take on some more terminologies of micro instructions. Okay, so instructions are nothing but they are the actions which is to be done by the MUP. MUP stands for microprocessor. Okay, tells what. So that is known as instructions. So the instructions, when instruction is given to the microprocessor, it generally there are two cycles. One is known as the fetch cycle. So I'm just introducing these terms in this lecture, so that once we start on with 86 classes, you are comfortable with these terminologies. Okay, fetch cycle means the microprocessor will take the instructions from the it brings the instructions from the memory, stores it in the instruction register which is within the microprocessor. That is the fetch cycle. Fetch cycle is just getting the instruction from the memory into the processor. In the execute cycle, what it does is whatever instructions were brought down, it will execute that. Okay, so this is the actual where the action takes place. Okay, so these are the two terminologies, fetch cycle and execute cycle. Okay, this is another block diagram which we will see in the textbooks. BIU, it stands for bus interface unit. Okay, so this is also part of the microprocessor. What it does is it keeps whenever an data is to be sent to a particular memory cell, it places that address of that memory cell in the address bus. Okay, similarly it gives signals of read and write. Okay, so along with placing the address data on the address bus, the BIU also will send the signals of read and write also, right? And then there will be a data bus through which the transfer of the data between the memory cells and the microprocessor takes place, and there will be an ALU and the control and timing unit which synchronizes the operations. Okay, so don't get perturbed and that you're not understanding the entire concept. Okay, I'm just introducing you to some terms of microprocessor. When we see 8086 from the next class onwards, and we'll take each one of them in detail, and how an address is placed onto the bus bar, how does the read operation takes place, when does it takes place, what are the timing diagrams. So all this data will be discussed in detail. Okay, so yeah, you already got the answer what is BIU. So the all this data. So right now we are just I'm introducing you to some terminologies. Detailed operation specific to 8086 will take on from the next class. Okay. So this is another block diagram which is there in the textbooks, you will find. So in this, the only change which is brought in is it's shown here that there are various registers within the microprocessor also. Okay, apart from ROM, RAM, some information, and the ALU doesn't really compute data taking directly from the RAM and ROM. Okay, those data are generally brought into some registers, and from here it does the computation, right? And you will be also able to store the data into the RAM and ROM also from the ALU. So this is just showing that there are some registers also available. EU stands for the electronic unit again here, right? So this is another block diagram which you will find in the textbooks. Okay, and then we will hear a lot of these terms, bus, address bus, data bus, and all. Okay, it is nothing but a set of wires, right, which is interconnecting the processor with the memory. So whenever we see, memory could be RAM, ROM, or like in 8086 there are 20 lines. Okay, so 2 to the power of 20, that is around 1 mega different cells, memory cells can be addressed. Okay, so to access those memory cells you require address bus. So once you place an address bus which is a 20-bit data, that particular cell will be activated, and then the data from that bus, from that cell, will be brought to the processor through the data bus. Okay, so data bus essentially, again, all this bus means it's just a set of wires, okay, which enables transfer of data from one port to other. So address bus essentially is an one-way bus wherein the microprocessor activates the places the address bus data, and that a memory cell, or it could be an input output port corresponding to that address bus will get activated and will get connected to the data bus, and from the data bus the data gets transferred. This is a two-way bus, that is, the data can be written into the memory, or it can be read from the memory, or it could be data could be written read from an input output port, or it can be written to an input output port. So these are some of the terminologies. So this is just when you see when we say bus, it essentially means it is a set of interconnecting wires. Okay, and there are some control signals, like these are some of the terminologies we will use. MEMR means memory read. So whenever this memory read signal goes high, the memory, whatever memory corresponding to the address which is placed here, right, and that will be made ready for a read operation. Similarly, MEMW, this means memory write. So whenever the control signal memory write, there will be 4 different wires here. So when this memory write signal goes high, so whatever is the address data is placed in the address bus corresponding to that memory cell, that will be made ready for a write operation. Okay, so similarly, input output read or input output write. So IO ports, so you can connect IO ports also. So whenever an IO port is connected and you want to read something from the IO port, you give IOR as a high. Similarly, if you have to write an data onto the IO port, you will give IOW signal as a high. So these are some of the terminologies which we are going to use it in the next from the next class onwards. Okay, then coming to memory. So this we learned it in our digital class also. ROM stands for read only memory. It is non-volatile. That is, even when the power supply is not there, still this information will be available in the ROMs. So we saw that EPROMs, PROMs, different kind of ROMs in the digital class, right? So all the microprocessors also, we can connect some of the address lines can be connected to a ROM chip also, and RAM is it's an volatile. So whenever the supply goes off, okay, this memory
whatever is there in the memory, that data gets lost. Okay, so it's no more available. So as long as the power supply is available, the RAM will store that data in that. Okay, so that is the RAM and ROM. Okay. Okay, coming to the processors, processors can be classified into complex instruction set computer or a reduced instruction set computer. Complex instruction set register, again, essentially it can take operands from ALU from the register and the memory, whereas RISC, it takes only from the register. Okay, I'll make it slightly more easy for you. If you see, if there is an instruction wherein you have a data, some data in memory A, okay, it could be RAM or ROM, and in memory location B there is some more data. You need to multiply both these data and put the result in A, right? So in an as a CISC processor, you can give a direct instruction, okay, multiply AB, right? So it will take the information from A, do the computation and do, whereas in an RISC you can't do that. So you will have to give a separate instructions to the processor. So essentially you will have to first load the A data into one internal register. Again, you have to give a separate instruction for to load it in the B, and then multiply instruction and then you store instruction. Basically, these microprocessors, CISC microprocessors, are complex in nature, and you can give you can 86 is an CISC. Okay, you can give such instructions in 8086 also. We'll see the instructions. So it can take a very complex instruction, break down into number of small instructions of its own, and in each clock cycle it will execute one instructions. Like in 8086 also, some instructions will require, say, 8 clock cycles. Some instructions will require 2 clock cycles. So based on the instruction, the number of clock cycles required will be different. Okay, some operations will require only 2 clock cycles, some instructions may require 4 clock cycles, some instructions might require 6 clock cycles. So in C, whereas in an RIC, generally in the mobiles and all, SOCs and all, they work on RIC, where it will just use 1 clock cycle and you will have to give small instructions. So here if you see, it is pretty fast. It will keep doing small instructions, but then it cannot do a very complex operations. It will do small operations. So these are best suited for applications like mobile and things like that, right? Whereas CISC is since backward comparison instruction set. You can give these kind of instructions in a CISC computer also. You can break it up and give it also. So that can be done. That can be done here. Okay. All the microprocessors are generally they are all CISC only. Okay, RISC is a relatively a new concept. I have a small video of 3 minutes. I'm just going to play that. So hopefully all your doubts on RISC and CISC will be cleared. Okay, it's just a 3 minutes video. I'll just play this. You may now pause this video and watch the video from the link which is provided below. This will give you a fair idea about the difference between an RISC processor and CISC processor. Okay, we'll discuss a few more terminologies. We'll see what is pipelining, instruction pipelining. Okay, suppose this is a set of instructions which the microprocessor has to do. It requires 9 cycles. Okay, the first it is going to fetch an instruction, right? It is going to decode it, and then it is going to execute it. Again, it is going to fetch the second set of instruction, decode it, execute it. Fetch, decode, execute. Okay, so 3 set of instructions. It requires say 9 clock cycles, suppose. Okay, what does pipelining mean is, like the first instruction, it is being fetched, and then it is being decoded, and then it is being executed. While the first instruction is being decoded, okay, the bus interface unit is going to fetch the second instruction and store it in a temporary register. It will keep it ready for the next cycle, right? And as soon as this gets free, the first path, the second instruction is ready. So you are essentially saving the number of clock cycles. Okay, so this is known as a kind of parallel operation, right? The ALU is here, right? The ALU is doing the execution. So ALU is doing only one execution at any given time. If you see at this instance, the ALU is executing the first instruction. At this instance, at the fourth cycle, the ALU is handling the second instruction, and in the fifth cycle, it is doing the third. It is only, there is only one ALU. It is not a multi-processor. Okay, it is the same processor. Okay, but the thing is, you are staggering it. You are doing kind of parallel processing. That is, you are keeping the data ready for the ALU so this is known as pipelining. So 8086 essentially does is a pipelining architecture. What is pipelining? Is it understood? There are some temporary registers where the instructions, while the instruction is being decoded, the first instruction, the next instruction will be brought and placed into a temporary register. Okay, and while this is being executed, and this instruction will be decoded here, and the third will be being fetched. So is the pipelining process clear to all of you? Let us now see a few more technical terms of microprocessors. This is actually classification of microprocessors. Okay, so as per the classification, the first class of microprocessors are known as SISD. It stands for single instruction, single data systems. Okay, in which the processor, there is a single processing unit. It takes instructions serially from instruction pool, and there is a single data pool. So this is known as single instruction, single data system. So here you see sequentially each instruction is loaded into the PU and it is computed here, right? The second kind of microprocessors, the second classification is known as single instruction multiple data system, right? In which the instruction pool is single and there are multiple processors which are doing parallel processing, right? So the instruction is taken out here, single instruction, whereas there are multiple data systems, right? Suppose you have you could have multiple RAMs. Okay, in the single instruction, and it can be broken down into small instructions, and each instruction might depend on a different data pool out here, right? It could be different RAMs altogether, or it could be different segments of the same RAM. So it is a single instruction which is broken down into small instructions which are independent to each other, and finally the results could be compiled again and back to get the final single results. But essentially the single instruction can be broken down into small instructions and they can run parallelly. They are mutually exclusive, and there could be data from different segments of the RAM or from different RAMs altogether. So these kind of processors are known known as single instruction multiple data systems. The third type of system is known as multiple instruction single data systems, in which in this you have the data pool is single. There could be single RAM, but there could be multiple instructions which are being done parallelly. Suppose you are there could be different programs running in the microprocessors. Okay, there could be multiple instructions, right? There could be one processor could be processing a Word document, the other could be processing a Excel document, like that. So here you see there are multiple instructions, but the RAM is it's a single RAM or a single data pool where the data is coming from a single pool, but the instructions are they're different instructions altogether. They're not the subset of a same instruction. The instructions itself are totally not related to each other. So it's known as multiple instruction single data systems, right? And the last and final one is the multiple instruction multiple systems, where you have different instructions running in different processors, and also a single instructions being broken up into multiple processors, and then you have the multiple data pool. So these are the four kind of processors which we have. They have been classified like that. So just for academic point of view, I'm just mentioning there are four types of okay. And then the next thing which we'll keep hearing about is multi-core processors, right? So now you see there are two cores out here. This is an example given here, but we have a quad-core processors or 8-core processors, right? So we have servers which have got more than 16 cores also. So you is this an example where there are two cores are there, and there is a control unit, and so the computation is done by these two different cores, right? They are kind of two processors itself. Okay, they can independently do it will have its own, each core will have its own ALU, and it can do a lot of computation on itself and independent of what is happening in the other core. So an instruction can be loaded into both the cores. A complex instruction can be broken into small instructions, and parallel processing can be done here, right? So many there is a popular belief that these multi-cores help in speeding up the operations, right? So it will enable fast processing. Yeah, that is very, very true. But there is also dual cores or multi-cores help in reduction in power. Like I said in my first lecture, power is a major issue, right, with modern day processors. So multi-cores help in reducing the power also, right? So how it's going to reduce the power, I'm going to just explain you that aspect also, right? So this is a simple inverter which we studied in our digital class, right? So it's an inverter, CMOS inverter. This is an NMOS, this is an PMOS. So whenever the input signal is going from high to low, this PMOS, when it is high here, it's an inverter, it will be low here. So the node capacitance out here will have no charges. Whenever the signal is going low, this NMOS will be switched off and this PMOS will be switched on. So from VDD through this PMOS, this node capacitance will get charged to VDD, right? So if I try to find out what is the energy which is stored in the capacitor, that we know this is a common electrical derivation, where the energy stored in a capacitor is half VDD square CL, right? So this capacitance, as soon as initially the output was 0, okay, input was 1, the input has gone from 1 to 0. Now if it has gone from 1 to 0, the NMOS has switched off and PMOS has switched on. Now since the PMOS is switched on, this capacitor is going to get charged to VDD. So the energy which is stored in the capacitor is half VDD square CL. So so if you see, but what is the energy which is taken from the power supply? So if you integrate the voltage into current and the voltage and the current, right, then you get the energy which is taken from the power supply. So if you do that, you will get VDD square CL. right? So this is the energy which is taken from the power supply. This is the energy which is stored in the capacitor. So you will find an half VDD square is missing. So what about the other half VDD square? That is dissipated as heat in the PMOS. Okay, while this capacitance is getting charged, so current is flowing here, right? So this is an equivalent resistance. So I square R, heat. So for every charging of the node, so in the PMOS, this is the energy which gets dissipated as heat, half VDD square CL, right? Similarly, when the input, now if it goes from 0 to 1, this is switched off and this is switched on. So whatever was the charge which was stored in the capacitors, node capacitors, that was half VDD square. So that gets discharged to ground. So again, energy, whatever is energy cannot be destroyed, right? So it gets dissipated as heat in NMOS. So during discharge, half VDD square CL energy gets dissipated in NMOS. So if you see, that is the energy. If I talk about power, so frequency is nothing but the number of times it's happening in a second. So the total energy which gets consumed in this circuit is frequency into VDD square into CL, right? So this is the power of an CMOS inverter. So this is true for any CMOS logic circuit. Okay, so essentially we need to remember, you don't have to remember these derivations and all for this particular course. Okay, this is from advanced VLSI design course. I just wanted to give you a brief idea about what is the power which gets consumed. It is a function of frequency, it is a function of VDD square, and it is a function of the capacitance, right? So this is the multi-core processors. This is for a single inverter. So now let's see, suppose I have a single processor. Now the power, this one is the switching power. Okay, now if you see in this equation, one neta factor has been added. That is nothing but the activity cycle. That means this is the frequency, is the clock. So in every clock, the output need not change to 0 to 1 and 1 to 0, right? So neta is a factor which is proportional to the activity. So this is the total power which gets dissipated in a core. Okay, neta f clock CL VDD square. So this is a processor. Suppose I am operating at 100 Mbps, and the delay is the, once you give an input, the propagation delay of the processor, it takes say 10 nanoseconds. 10 nanoseconds is the time for it to do the processing, right? And 5 volt is the power supply required for this processor, and 16 milliwatt is the power. Okay, these are just figures, some random figures I have put here. So assuming this is good. Now instead of using a single processor, now I am going to use two processors, right, which will run parallelly. So since I am using two processors in parallelly, okay, I can reduce the, I can increase the time. It is taking 10 nanosecond time, right? So now I can actually decrease the I can use a processor with an reduced voltage VDD. Okay, instead of 5 volt VDD, now I am going to use 2.5 volt VDD, right? So and I'm going to reduce the clock frequency also, and the delay will be more here because the VDD is reduced, and it will work slowly now. Okay, this will have more delays to 20 nanosecond, right? But I'm running in parallelly. So the same instructions which was initially I was giving at 100 Mbps and it was taking 10 nanoseconds for it to compute. Now I am going to put into two parallel processors, right? Because then each processor can take 20 nanosecond, right? Because the delay has increased, but I am using an parallel processing. So only half of the instructions this need to be processed. Okay, earlier for one particular big instruction it used to take 10 nanoseconds. Now corresponding to this 10 nanoseconds it is 20 nanoseconds, but then since I am using parallel processing, I am only giving half of the instructions to these processors. So this will also essentially take only 10 nanosecond, and this will also take 10 nanosecond, and then I add these two data results, subsequently. So finally I will get the result in 10 nanosecond. Okay, so the voltage has been scaled down to 2.5 volt, right? And and the frequency is also scaled down to 50%. Now if I use this formula, if you see VDD is reduced by 2, okay, and the clock is also reduced by 2. So so if you say it is VDD square, it is FCL. So clock is reduced by half, VDD is reduced by half. So overall, since it's a square, overall power as compared to this will come down by 8. So instead of 16 milliwatt, this processor will require only 2 milliwatt of power. Similarly, this processor instead of 16 will require 2 milliwatt. So now we are going to add these two outputs and get a single output. So the total power will be 4 milliwatt. So 4 milliwatt. See, this is a single core, this is a dual core. Both are doing exactly the same function. Final, it is operating at 100 Mbps speed. This is also operating at 100 Mbps speed, right? So and it's giving an output at 10 nanosecond. This is also giving it 10 nanosecond. Only in this case, what we are doing is we are using half the VDD in both the processors, half the clock, and then adding up the computational results out here. So by using an multi-core option. But since and then we take the total power. Total power is just an algebraic sum of these two powers. But since we are reducing the VDD, okay, there is a square available here. So this comes to 2 milliwatt instead of 16. Similarly, this comes to 2 million, and if you add, it is 4. So from here to here, you see it is 16 milliwatt, and this is just 4 milliwatt. So almost 4 times lesser power it's using, right? So this is a huge gain in power. So so in this case, what we have done is we have kept the speed constant and see to that the power is reduced. Okay, or in other words, you can say if you keep the power same, you will get a high speed. So so that is how these today's modern day processors they see, where whenever there is a huge task which is coming, instead of loading onto a single processor, if you split it into multiple processors, so that will take care of the power requirement and heat dissipation also. Okay, so we should not look at multi-cores processors as something which will increase the speed alone. Okay, it has much more to do in the power budget scheme, right? Multi-cores. So you need to understand that. And there are many processors when they the VDD is also scaled dynamically whenever the processor gets heated up. So the VDD is slightly reduced so that the speed reduces and the heat is managed. And similarly, the distribution of the processors is also based on the junction temperatures of each of the processors. That is also closely monitored these days. So that is about multi-core processors. This is again one big picture which is showing there are quad processors, but there are now even this quad is outdated. There are 8 cores are available in most of the mobiles these days. Okay. So this is the last slide which was there in the course handout. So let me just cover it. Now, what happens when you turn on your computer? That we all know that initially since when you switch on the microprocessor, it has to boot and it has to load the operating systems, and also some instructions have to be given to the microprocessors. So there will be a ROM on the microprocessor board. In the ROM, those instructions are given, which will be there even when you switch off the power supply. So once you switch on the power supply, it will start reading it right from the ROM memory location, and in the ROM memory location, from what operating system is to be loaded, those kind of instructions will be written, and it will load those kind of instructions. It will go to those memory locations and start loading the operating system. Now the operating systems are generally loaded loaded in the hard drive, right? So when the microprocessor can't keep accessing the hard disk always for running a program, because that will take a lot of time and it will be slow. So whatever is the required portion of the program which needs to be run at a particular time, okay, only that portion of the hard drive, that data is fetched and placed into the RAM. So RAM is basically a temporary file location where the required information from the hard disk is brought and it is placed in the RAM. So RAMs operate pretty fast. Okay, you have DDR3, DDR4 RAMs. So these are HyperX RAMs are there right now. They're pretty fast. So these RAMs essentially take the required data, is used to bring the required data from the hard disk temporarily, so that the microprocessor can run that program from the RAM. So it is kind of an fast temporary hard memory location for the microprocessors. Okay, so these are some of the terms. I think with this we have finished today's class, and this slide I will share. It just gives you the evolution of the microprocessors, the dates and transistors and the clock speed. 1.4 till Pentium 4 it's written, and 1.5 gigahertz. Okay, so with this we have in the next class I am going to introduce 8086. In the first class we are going to learn about the basic block diagram, and then from there onwards we'll get into the nitty-gritties of 8086. Okay, thanks a lot.